Carl is, in addition to being CEO and technologist, also a maker. So let me start with the maker-in-chief.
Let me move on to one other thing that has me particularly interested, and this is this idea of generative design. And it's different than what we see going on in the world where we're going to capture something. This is a different idea in which it starts with the idea that computing is virtually free and it's virtually infinite. And if you had all the computing in the world, how would you design and engineer things differently? And that's what was the starting point for what we were thinking here. And at first we said, let's just test exhaustively. And that certainly yielded some results. But then we said, what we really want to be doing, because in the world of CAD, computer-aided design, I would say in the 30 years that CAD has existed, the computer has barely ever aided in the design of anything. It started, it's true. It started 30 years ago, and we did 2D documentation. We agreed upon a convention, and I made a blueprint, and I transferred it to you. Today, we do the same thing with 3D models. We document our ideas. We do not design in these tools. And the idea is we need to reach the place where these tools actually help us. So here's this idea of generative design. So imagine we have something, fills a space envelope. And there are two fluids in it, and they're going to pass by each other, and there's thermodynamic requirements about exchanging heat. And all we're going to talk is about a high-level specification of what we want. And now we're going to let the computer, and remember, we believe that computing is virtually free. So we're going to let it run for hours, thousands of hours, tens of thousands of hours. And there's the heat exchanger that the computer designed. So it's one of these interesting things. It makes a lot of designers, I'd say almost angry, that the idea that, but I look at it as it's just another one of the tools. It's another technique that we have that will start getting at it. What's interesting about this design and several others like it, it explores the space in a way that guarantees you a near optimal solution. And there are very few times. As a matter of fact, we did another one for a part of the motorcycle, an electric motorcycle. We were working on the swing arm, and we ran it through the same algorithm, and the result that comes out looks almost identical to a dog or a cat pelvis, except it has a hole on one side. And we say to ourselves, this has to be a bug in the algorithm. And it turns out, of course not. Unlike a dog or a cat, the loading on a swing arm on a motorcycle is asymmetrical because the chain is on one side. And so it was interesting because when I went back and you go to the Google and you look at the images, and what the Google tells you is that all the swing arms have ever been designed for motorcycles. Nobody ever picked up on this fact. So I think there are insights that we can learn and that we need to be a little less proud about letting computers start helping us design and engineer things better. Here's another example just like this. This is one, it's growing a structure, and this is for a hip cup. And the idea behind the hip cup was to make a structure in which the foam has pores that are pseudo-random in size. And the reason is that it's demonstrably better in terms of having the bone grow into that if it is pseudo-random as opposed to a regular structure. The body recognizes that as weak bone and grows into it much better than if it's a regular structure. So we worked with a customer on being able to do this. And really, the interesting thing that comes up in stuff like this is because this one will be different for everyone who gets one, all of a sudden you have to get the FDA not to approve a device, but the FDA has to approve an algorithm. And if you think it's hard getting the FDA to approve devices, getting them to approve algorithms is really hard.